Welcome to our channel Circuits Analytica. In this video, we will be discussing about inverting summing amplifier. A summing amplifier is a circuit whose output is proportional to sum of the n input signals. There are two types of summing amplifiers: non-inverting summing amplifier and inverting summing amplifier. For a non-inverting summing amplifier, output is proportional to sum of the n inputs. In the case of an inverting summing amplifier, output is the sum of n inputs but inverted. Let us consider a 3-input inverting summing amplifier. The three inputs are denoted as VA, VB and VC. RA is the resistance connected between input VA and inverting input of the operational amplifier. RB is the resistance connected between VB and inverting input of the operational amplifier. RC is the resistance connected between VC and inverting input of the operational amplifier. Non-inverting input is connected to ground. A feedback resistance RF is connected between output and inverting input of the amplifier. Currents IA, IB, IC and IF are the current flow through resistors RA, RB, RC and RF respectively. So in an inverting amplifier, non-inverting input is connected to ground. So we can say that the amplifier is in inverting mode. And as previously mentioned, there are three inputs VA, VB and VC connected to the inverting input of the operational amplifier through resistors RA, RB and RC. Let us apply KVL to the loop which consists of inverting input of the op-amp, feedback resistance RF and output. We can write V2 minus V0 is equal to IF RF. According to KVL, voltage at the inverting input minus output voltage is equal to voltage drop across the feedback resistance RF. So, mind the direction of current flow. Current flows from inverting input to output. That is why the equation is V2 minus V0 is equal to IF into RF. Equation number 1. For an ideal op-amp, AOL is infinite. That means differential input voltage VID is equal to 0. We know that differential input voltage is the difference between voltage at the non-inverting input and voltage at the inverting input. VID is equal to V1 minus V2. As the non-inverting input is connected to ground, V1 is equal to 0. As VID is equal to 0, that means V1 minus V2 is equal to 0. So V1 is equal to 0 as it is connected to ground. 0 minus V2 is equal to 0. That means V2 is equal to 0 and this condition is called as virtual ground. So substituting this V2 in equation number 1, we will get 0 minus V0 is equal to IF RF. Or we can write equation for output voltage V0 is equal to minus IF RF, equation number 2. So this means that output voltage V0 is proportional to current flow through the feedback resistance RF. Now apply KCL at the inverting input of the operational amplifier. There are 5 currents associated with the inverting input of the operational amplifier. The 5 currents are IA, IB, IC, IF and current flow towards inverting input of the operational amplifier. So for an ideal operational amplifier, input impedance is equal to infinity. That means current flow towards inverting and non-inverting inputs is equal to 0. So actually there are 4 currents associated with the inverting input of the operational amplifier. And these 4 currents are IA, IB, IC and IF. According to KCL, total incoming currents is equal to total outgoing currents. So IA plus IB plus IC is equal to IF, as IA, IB and IC are the 3 incoming currents and IF is the lone outgoing current. So this is equation number 3. Now let us write equations for currents IA, IB and IC. So applying KVL to the loop which consists of input signal VA, resistance RA and inverting input of the operational amplifier, we will get VA minus V2 is equal to IA into RA. That means IA is equal to VA minus V2 divided by RA. So due to virtual ground, we can write V2 is equal to 0. So IA is equal to VA divided by RA. Similarly, we can write IB is equal to VB divided by RB and IC is equal to VC divided by RC. Now substituting the values of IA, IB and IC in equation number 3, we will get VA divided by RA plus VB divided by RB plus VC divided by RC is equal to IF. So according to equation number 3, IA plus IB plus IC is equal to IF. Substituting the equations for IA, IB and IC, we can rewrite equation number 3 as VA by RA plus VB by RB plus VC by RC, that is equal to IF. So from equation number 2, we can write output voltage V0 is equal to minus IF into RF, that is equal to minus RF into VA by RA plus VB by RB plus VC by RC, as IF is equal to VA by RA plus VB by RB plus VC by RC. So we can write the expression for output voltage V0 as V0 is equal to minus RF into VA by RA plus VB by RB plus VC by RC. So if RA is equal to RB is equal to RC is equal to R, then we can write output voltage V0 is equal to minus RF into VA by R plus VB by R plus VC by R. So here R is a common term in the denominator. We can write output voltage V0 is equal to minus Rf by R into VA plus VB plus VC. So output voltage V0 is equal to minus Rf by R into VA plus VB plus VC. So if Rf is equal to R, then we can rewrite this equation as V0 is equal to minus of VA plus VB plus VC. So then this becomes a summing amplifier. So if feedback resistance Rf is equal to Ra is equal to Rb is equal to Rc, then the circuit becomes an inverting summing amplifier. If R is equal to 3Rf, then we can rewrite the equation for output voltage V0 as V0 is equal to minus Rf divided by 3Rf into VA plus VB plus VC. That means output voltage V0 is equal to minus 1 by 3 into VA plus VB plus VC. So the equation for output voltage V0 is equal to minus 1 by 3 into VA plus VB plus VC. That means the inverting summing amplifier becomes an averaging amplifier. So these are the expressions for a 3-input inverting summing amplifier. If there are n number of inputs, then equations becomes V0 is equal to minus Rf into VA by Ra plus VB by RB plus VC by RC plus etc. So if Ra is equal to RB is equal to RC is equal to RD is equal to etc. is equal to R, then the equation becomes V0 is equal to minus Rf by R into VA plus VB plus VC plus VD plus etc. If Rf is equal to R, then this becomes an inverting summing amplifier with n number of inputs, and the output voltage equation is V0 is equal to minus of VA plus VB plus VC plus etc. Applying another condition, if R is equal to n times Rf, then V0 is equal to minus Rf divided by nRf into VA plus VB plus VC plus VD plus etc. Or output voltage V0 is equal to minus 1 by n into VA plus VB plus VC plus VD plus etc. n number of inputs. So this is the equation for an averaging amplifier. Thanks for watching Circuits Analytica. Enjoy learning. Please comment, like, share and subscribe our channel.